Yeah, are you ready, guys?
Yes, of course.
Let's do it.
Okay, good morning, good afternoon, good evening, Dryden Aqua friends from around the world. My name is Philip. I'm one of the managing directors at Dryden Aqua, responsible for the American, Asian, and Australian markets.
Yes, good morning, everybody. My name is Dominic. I'm also managing director in the Dryden Group. I'm responsible for Europe and Africa. And honestly, I mean, it makes us really proud to see how many people participate live and also later on our YouTube channel. It makes us proud, but also gives us a very good motivation for our session number 4.
We'll give our best, huh?
Welcome. Yeah. I'm Jochen. I'm responsible for all water treatment applications, direct to water treatment. So call me anytime if you have questions about the use of AFM in water treatment.
Okay, exactly. And today's subject, we are talking about
wastewater.
So we are not want to waste your time. We want to talk about wastewater.
Excellent.
Wastewater. Yes.
Operators, start, please.
Start the engine, please.
Okay.
Perfect.
Here we go. Agenda, Jochen.
Okay, so
3 points, 3 simple steps.
Yes. Introduction. Then we talk about AFM. Then wastewater treatment case studies. Then oil and hydrocarbons removal.
Yeah. So introduction, wastewater, oil removal. These are the key ones.
Okay, and the rules, as always, please use the Q&A function to ask your questions as we go through the presentations. It will be recorded, so you will be able to watch the presentation on our YouTube channel. And that is the YouTube water treatment channel that we have.
So we have 3, Dryden Aqua. Water treatment is a channel that we talk about. And it would be great if you subscribe to it so you get always a notice to it. This is not wastewater. This was drinking water.
Exactly, yes. I just want to give you a quick update here. We had in our last webinar presented this case study. Now we have some first figures here.
And we said it's in operation. It just went in operation, but there are no figures. Now we have figures. Okay, there are
not
just
too
3
many
days.
Yeah, but
how look the figures?
Really good. Yes, so I'm really impressed about the figures. They started with really low 0.5 NTU, and then we reached 0.15 that has been measured just 2 days ago. That's really, I'm really excited about these results here.
Okay, let me precise this a little bit. You know, with sand and coagulation, they are on 0.3 turbidity.
Yeah.
And here we have purely AFM.
Yeah.
No coagulation, 0.15. I hope that will stay like this. We do not know, but yeah, that was a chart that you see. We try to bring you back the numbers if we have them.
Yeah.
Okay, let's talk about quickly introduction.
Okay, short introduction again to Dryden Aqua. We started about 30 years ago in the aquaria and aquaculture.
Dr. Howard Dryden.
Yes, that's Howard, who is a marine biologist. And
the best chemist I've ever met.
Absolutely. We then developed into the swimming pool industry, which is about 50% of our business today. And a few years ago, we started to focus and develop the water treatment industry, which is about 40% of our sales today.
And the reason for this, because this market is much bigger. In the first few years, you guys didn't want to talk to us, but now you're here, you want to listen to us. This is great. So we believe this is very short. This is the dominant factor.
Yes. Okay. AFM is produced in 2 factories, one in Scotland, one in Switzerland, here where we are. You can see this behind us here.
This is Switzerland.
Factory. We have a sales office in the US, where we also have a logistics space with 5 warehouses.
Are you sure?
Yes, I am.
Yes.
And we have an office in China, in Shanghai, also with a warehouse. We also have a sales office in Germany that serves mostly the Eastern European and Russian market.
Sorry to say you're wrong. It's not a sales office, just a logistic base for East Europe for small quantities. Big quantities come directly from us. Here you see the 2 factories, you know, the older ones, which was just upgraded 5 months ago. We invested another 5 billion.
Wow.
5 million.
That would be really inflationary.
Yeah, absolutely. That's the next time. And here really on the one that we are on both, we are very proud, but the one which is very green, you know, full with solar powered, fully solar powered, rainwater, sludge, etc. Short introduction, who we are, what we do by our founder, Dr. Howard Dryden.
Dryden Aqua is one of the largest manufacturers of water filtration media in Europe. Our activated filter media, AFM, is verified to be the best. We are marine biologists and provide sparkling, blue, safe water for over 200,000 swimming pools and clean drinking water for millions of people in Europe, in Africa and Asia. AFM doubles the performance in sand filters and negates the need to invest in new infrastructure. It future-proofs water treatment. Dryden Aqua can process 50% of all the glass bottles in Scotland. The glass is fed into a hopper, all the metal is extracted, and the glass is washed to remove the impurities at 1200 degrees centigrade. The clean glass colour sorted to remove the clear glass and ceramic. The glass is spun in a cyclone and the particles are sieved to make the different size grades. The glass media is activated by a two-stage chemical process followed by a thermal curing process. AFM is packed into carbon-neutral plastic bags exported around the world.
Well, perfect. Can you hear us again? Oh, very good. So I really love this video. It's an old video. The production that you see is the old version. So this is more of the history channel. But I like, how Howard explains it, and he's a great guy. It's an unbelievable scientist. Okay. Let's talk about sand filters. Sand filters, as you all know, it's a very good mechanical filter, but it's also a very good carrier for bacterial growth. And how this happens in water, we have bacteria, heterotrophs, autotrophs, and especially the heterotrophs, they try to reach a surface within seconds, because otherwise there is maybe oxidation, etc. And to protect themselves, they will excrete a mucus. Or EPS, as I learned it, extracellular polymeric substance to cover themselves. We call it a biofilm. This bacteria covered with this slime, we call it a biofilm. And if temperatures are nice, heterophobe bacteria, they can double every 30 minutes. So it goes really exponential. And that can create some problems. Now, the biggest surface that we have?
Yeah, so the biggest surface that we have in a system is actually the filter media itself. If you look at sand here, 1 meter cube of sand has a surface of 3,000 square meters.
That's a lot.
That's a lot. That could be 90, 95% or more of all the surfaces that are in contact with water. Yeah. In addition to it, like Dominic said, sand is a natural breeding ground for bacteria, right? So this even amplifies this problem.
Yeah, in aquaculture, often we use fluidized sand baths, as biofilter. Yep. And the problem is, very often you dose then chlorine before the sand to keep it free of biofilm. That will not work, Chlorine cannot penetrate the biofilm. It has to oxidize from outside to inside, and by this it's losing concentration. So even if you go with high chlorination, you will remove maybe 99.99999 whatever %. But the moment where you have 1 or 2 survivors, the conditions are good, enough food, good temperature, you're back in problem. And very often in chlorinated system, especially in permanent chlorinated system, after a period of time, you can create a bigger biofilm problem than before. So the process of natural selection, you kill the weak ones, the survival of the fittest, the strong one will have all the space. What's the problem with this?
So biofilm in the filter media after a while leads to coagulation of the grains. So they start to stick together, they form lumps or clumps, and the filter media at some point starts to channel, which means which means you have unfiltered water that will get through your filter. Now, this happens, you know, for example, in a wastewater treatment application, this happens much sooner than in clean water filtration, but this can happen anywhere between, you know, 2 months and 6 months.
12 months maybe
Yeah.
in a drinking water. Yeah. The
Yeah.
more the load, the more the temperature, the purer the backwash regime, the more you have this.
Yeah.
And if it's channeled, you bypass your filter media.
Exactly.
You have highways, you bypass it.
I
It's
mean,
not,
especially in wastewater treatment, we talked today, this is very important to
Yeah.
understand.
and this is, you know, where from time to time when these opens are channeling, you know, have a breakthrough of biofilm formation. And this is also when you have a high increase in turbidity in biomass and suspended solids. It's just your filtration is not anymore longer reliable. And this is why, especially in wastewater, it's really important not to fight with chlorine against this problem, to find a solution at the source and to go for a bioresistant filter media.
Yeah.
And the best I know is AFM.
Yeah.
Why this?
So how or why is AFM self-sterilizing? What happens on the surface of the AFM grain is a catalytic surface reaction. This is when small amounts of oxygen in the water react with metal oxides that are on the surface of the AFM grain. This will form hydroxyl radicals, small amounts of hydroxyl radicals.
These guys you are turning here.
Exactly, yeah. But they have a very high oxidation potential, and they will oxidize bacteria that will try to attach on the surface of the grain. Therefore, there is no formation of biofilm.
Exactly. These guys do not reach this. They are gone. They are gone. And therefore, I think you mentioned it. This is why we use only green and brown glass, because they contain this metal oxide. So we reject the white glass, we color sort it out and just use this. And because this is a catalytic, did you mention this?
Yes. Yeah.
Okay. Sorry.
But it's important. No, it's an important point, because it's the metal oxides, right? But it's also the surface. So the activation process that we have increases the surface area. And because you have a much greater surface area, you're also producing more of these free radicals, which makes it more bioresistant than any glass filter media that's on the market.
Yeah.
That's important.
It's the only one which is really bioresistant.
And here you can see new sand, new AFM, fresh material. Then after a couple of days, they grow on sand. As you can see here, on AFM, even after 5 years, we have no growth of bacteria on the surface. So you can see that here in the bacteria count. And you see that with this one, we can avoid really the clumping and channeling, which then achieves the important good performance of AFM.
So this is sand, bioactive. This is AFM, bioresistant. And what does this mean? You know, this is a study that we got from our friends from Spain, from PS Water. Patrick, I don't know if he's on the call, but that was a really good one. You know, they had a wastewater treatment, 2 completely identical filters, one filled with AFM, one filled with sand. And here you see the sand pattern. Here below you have tiempo, the time. And here you have the loading rate. The loading rate here is just the increase of the pressure of the delta P. And what you do here, you know, they just measured the delta P. So the filter was filtering here, had a breakthrough for whatever reason, until they reached 180 millibars pressure increase, and then they backwashed. And they did this in the next cycle. And here you see in the 3rd cycle, nothing happens. There is no pressure increase. You know, always stay on the same pressure, and that means it's channeled. It's not filtering. If you don't have a pressure increase, it's not filtering. And here it becomes a little bit more regular, and this is exactly what it is with these channels. You know, sometimes, you know, they open and then there is no filtration. And if you compare this with AFM, again, same filter or equal filter, similar, similar filter.
Side by side, right?
And you see here pressure increase. It's really going up. Bam, backwash, pressure increase, backwash, pressure increase, backwash. It's like a Swiss watch. Bam, 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 bam. You also see there are more cycles. You know, we have here 15 cycles. Here we only had 11 cycles. So the better you filter, the more suspended solids you take out, the more often you have to backwash. But really in wastewater, it's important that you have this pattern and not this pattern.
That's key.
Okay.
Filtration performance and backwash requirements.
Okay, so we are talking about, you know, how well AFM is performing. Obviously, we have everything has been independently tested by a French institute called IFTS. And what again does that say?
Institut de la Filtration et Techniques Séparatives.
Oh,
exactly right.
Huh?
So this is very important. This is a white paper that we have, and what we see here is the performance of sand versus different grades of AFM. What we do is we put the line at 95%.
Yeah, that's our threshold, yes.
Yes, of removal performance. And then we look at the particle size removal. And what we see with AFM NG grade 1, we see a 95% removal down to 1 micron. And with AFM standard grade 1, we see it down to 4 micron at 95. Now, if we put this in comparison to sand, then you will see that sand, and this is a high quality fresh sand, so it's not a coagulated sand after, you know, 4 or 6 months, performs down to 20 micron. Now, 1 micron to 20 micron, is that much?
No, that's probably a global world.
Is it? Yeah,
it's
I
huge.
think
Galaxy,
so too.
maybe.
It's huge.
It's huge.
And this sand was 0.5 to 1 millimeter, so quite a fine sand.
Yep.
We also have here the AFM NG. You know, they only can measure down to 1 micron. So honestly, where we are on the 95, we do not know. Might be 0.5, might be lower.
Yeah.
So that's one that we use in very clean water applications, or if we don't have enough of backwash velocity, then we compensate with this. One word, AFM NG is relatively new on the market, 2-3 years. Very good for organics. It's hydrophobic, and for many applications, AFM standard is something. It's high negative charge. It's hydrophilic. That we will see with oil or sugar, what I just had this week. And especially for heavy metal removal. These are the differences.
Yeah.
So
very important. These tests are done at 20 meters per hour.
Oh yeah.
Filtration velocity, which is very high for these applications, but there's a reason for that, right? Usually on water treatment, we're a little bit lower than that. So the performance will be
more
even
10 meters.
better, even better performance. In pools, we live in a 30 meters per hour world. So we took the middle here.
Yeah, we want to save money. All these tests cost a hell of money. Here, by the way, let's talk now about backwash. And here you see, this is ISTS, Institut de Filtration et Techniques. You know what I mean. It's early morning. And here, this guy here is backwashing. And this was really AFM. And here, you see bad expansion. So yeah, you're backwashing, you need a certain velocity. Here it was 45 meters per hour. This was still the old AFM standard, old grading. And you see, how the bed expands. And really, we want minimum 15%, ideally 25%, or let's say the bigger the better, that you have a bed expansion, that you bring up the particles to the top of the filter bed, and also to wash them out. Philip, you want to add something?
Yeah, so in order to expand the bed by 15 to 25% using AFM in a wastewater application, you really need a backwash velocity of 40 meters or greater. Now, if you watched our session before, you saw that you could start at 20, 25 meters and higher. It is higher here now because we have to evacuate large solids from the filter bed as well. So you do need a higher backwash velocity. So 40 meters per hour is what we recommend. Now, this in comparison to sand, because AFM is about 20% lighter than sand. With sand, you would need, a minimum 40 to 60 meters per hour to get the same expansion.
Yeah, exactly. It always depends, on the size grain. The bigger the size grain, the more velocity you need. But if and on the shape, but we have an ideal shape, and usually sand also has quite a good shape, because sand is more heavy. It's 1,500 kilograms per meter cube, and glass is 1,250. You need 20% less of backwash velocity. Now, I know a lot of you guys out there, you're backwashing your filters at 10 and 15 meters. Maybe you don't want to hear that, but this is wrong, completely wrong. And you would see that, if you have a side glass, you would see there is zero bad expansion. And to backwash it, you remove a very small amount of the particles. But it's important that you remove all of them. And it's like a bin, filtration is like a bin. You collect the suspended solids, and then you have to empty it, and you have to empty it completely. And in backwash, it's opposite to other things in life. It's short and fast is better than slow and long, because you need these drag forces, especially in wastewater, especially in heavy metals, that you have enough of drag forces, enough of velocities to bring them out.
I mean, the same for oil, which will be shown later.
Yeah, absolutely. By the way, there is a mistake. That should be 50 to 60.
Should be 50 to 60.
So 20% more.
So maybe a word about air purge.
Yeah,
with sand, because it is biofouled, you need to air purge to scrub off the biofilm. And do this in combination with water backwash as well. AFM, because you have no biofilm, you do not need to air purge.
Yes, and this is also why often you have to backwash sand at the same velocity a lot longer, because you really have to rip off this biofilm first with air, water, only water. Also, a lot of people think, well, I do air, water, and so that's compensate, and then I don't need a high backwash velocity. Again, this is wrong, because with the air wash, with the air purge, you mix up the filter bed, and to reclassify the bed, you need a high backwash velocity to have this bed expansion to reclassify the bed.
Good. Yep.
We have to go on,
Next.
I know. But you see, this is how it should look like after a couple of minutes.
Okay, let's look a little bit further here. So we talk about wastewater. So wastewater contains a lot of suspended solids, or organics, or even oil. Yeah? So to remove this, in these applications, we really recommend that you do first a step of coagulation, flocculation, sedimentation, and then you have a decantation or overflow, where you'd really then get a much better quality for the treatment by AFM. We talk here especially like if you have metals more than 10 milligrams per liter, heavy metals, or suspended solids load more than 100 milligrams per liter, we really recommend that you do first a step of removing most of these suspended solids.
I would even recommend it at 50 milligrams per liter. Gravity is the cheapest way to filter. That's the cheapest one. And AFM is fine filtration. This is the polishing step. It's not the heavy filtration. Otherwise, you have to backwash the filter, I don't know, every half an hour. And that's probably not what you want to do. For us, it's great, so we can sell more AFM and more filters.
Yeah, and you need more filters, yes. That's actually a problem. Right?
So let's talk about the loading rate.
Loading rate.
You want to take this, Jochen?
Yeah, loading rate. So this is, as I just mentioned before, you want to have a lowest possible loading rate to have a long run phase of your filter, to have a very good quality of your water. So what does the loading rate tells us? You can see here on the screen that we have a loading rate for grade 1. That's grade specific, of course. So grade 1, we have about 2 to 6 kilos. This is depending on the particle size distribution. As finer as the particles to be removed are, as more depth filtration you have more capacity in your filter.
Sorry to interrupt you. I think you're already one step before. Let's quickly explain what we see here. He's so much full of energy and so much in the details, but not all our viewers are. This, again, was a test done by IFTS when they tested AFM standard, grade 1 and grade 0. And here you see the injected mass, which they gave, and then looked at what point you had the pressure increase. So here 200 millibar, and here you see with the 2000 grams per square meter, you had a pressure increase. This was done again with this 20 meters per hour of velocity. And this is not telling you the truth. If you go down to 10 meters, the loading rate would be much bigger. Also, what you see here, the red curve, 500 millibar, this is not if you reach a differential pressure of 500 millibar. This is if your differential pressure increases by 500 millibar, increase by 500 millibar. This is the time really to backwash your filter. If you don't backwash it, you risk that you have a breakthrough.
So your starting point at 200, then your pressure goes up to 700. That's then
and your time. If you start with 300, you go up by 800. I know some people go up with 1000 millibar. But, you know, at 600, 700, 800, it might be through the pressure you have once a breakthrough. So these are very conservative numbers that we also see in the other one. We are with our new lab now, and we wanted to have it ready for today, but yeah, something failed. And this is why we don't have it yet, but we bring this more and more, that we test now in our new lab at different velocities, all the loading rates. Yeah. But if we take this, and this is also a table, or how you call it?
A table, yes.
Yeah, from our IFU, from our manual.
Yeah, here you can see actually the load rate at different velocities, as you were just mentioning before.
Yeah, so here we have the velocities.
Yes, exactly, velocities, and we have different suspended solid removal rate at different velocities. So as an example here, if we go to 10 meters per hour.
So here 10
meters per hour. Then we typically for 4 hours, you can have a 50 ppm of suspended solid load rate that would equal to 4 hours backwash frequency.
So if you are on 10 meters and you have a suspended solids of 50 milligrams per liter, you would have to backwash the filters every 4 hours.
Every 4 hours.
And that's really worst case scenario, right?
And this comes from this data here. Now, again, in reality, because you're on 10, the reality will be bigger. How much bigger? We do not know. Yeah. It also, as you mentioned, depends a little bit on the particle size distribution of the suspended solids.
The same case here, if you have 10 ppm instead of 50, you multiply actually your time by 5, 4 hours by 5, so you end up with 20 hours. That means once a day you would have a backwash, which is kind of a normal backwash cycle under such suspended solids load.
Yeah, so adding anthracite will extend your run phase by a factor of 4.
Exactly, as you can see the second column here, adding anthracite, we actually multiply by 4 again. So that means on the same condition, you could actually even run then like more a week until you have to do a backwash.
But according to this table, at 10, 50 milligrams per liter suspended solids, backwash every 4 hours. If you go with 250 millimeters of anthracite every 20 hours, are these hyper precise data? No, they are not. Again, this depends on the particle size distribution. And we will come back, you know, with more precise data, but it's a good indication. And who else give you these indications? I don't know anyone.
Yeah,
I don't know anyone.
Yeah.
Don't be worried about this. Come with your projects, give us the data, suspended solids, raw water, what you want to achieve, and then we help you in the process design. Not in the detailed design, that's up to you. We don't want to take your job. Don't be afraid. We are helping you just with the filter media, with the software, optimizing the software.
So a quick look at operating parameters and design limits. If we look at, you know, the yellow section, which is municipal and industrial wastewater, then we recommend filtration velocity between 5 to 10 meters per hour.
Because of the high load.
Exactly. And you can see how this compares to other water sources.
But here in heavy metals, because of absorption, and here we can go higher.
Wastewater.
Again, this is over the dump routes.
Usually the lowest. If we look at backwash velocity, this is what we said before, 40 to 50 meters per hour.
Equal to heavy metals because heavy particles.
Heavy particles that need to be evacuated from the filter bed.
And you see in groundwater and in surface water cooling, it starts with 30. The red one is if you have an existing one where you only have 20, we compensate it more with grade 0, then we can go down to 20. But we do this for you.
The next one is backwash duration, also very important. So backwash duration and backwash velocity. So for wastewater, we recommend 4 to 5 minutes.
Why this? Because you see this also goes cross-linked to this.
Exactly.
So let's simple example. Let's imagine you have 60 meters per hour of backwash velocity. That's 1 meter per minute. So if you have a 2 meter filters from the nozzle plate to the top diffusers, the water needs 2 minutes to go to this, plus 50%, some safety margin, 3 minutes. If you have 30 meters, you need 2 minutes for 1 meter. So you need 4 minutes for 2 meters. Plus 50%, 6 minutes. And this is where these numbers are coming from. So we don't take it over the sum. This is calculated. By the way, the formula comes from Philip. Thanks.
Well, I like easy, right?
Yeah, absolutely. And here 29 minutes, that also makes sense. Huh?
Okay. This information is obviously also in our IFU rinse duration. Now for cooling water, there's no need for rinse.
Because it's a recycled
wastewater,
system.
you know, we recommend again 2 to 3 minutes. Why is that?
Because at 3 minutes you need here to go through the filter at that filtration velocity that you have up there. Huh?
Exactly. Huh?
Yeah.
And then the pressure increase 500 millibar as a rule of thumb.
Yeah. You can do before, but we recommend this is the time to do a backwash.
Yeah, here, backwash curves.
Yeah.
So as we said before here, we have different grades. That means we have different expansions. If you take here, like the first one, AFM grade 1, we have one, let's say at 30 meters, we have 25% bed expansion. The same for grade 0. If you go to 25 meters, we have actually a much higher bed expansion, maybe up to 30. But what
go on 20 or maybe again,
20. But important is that typically we have a combinations of different grades. So that can see we have a curve of different grading, like here 50-50, grade 1 and grade 2. That is a combination of the backwash velocity and bed expansion. But we will consider that in our calculations. We will happy to do this for you. But very important is these curves here are also in our IFU, so you can really take a look by yourself. What do you need at different combinations or layering of AFM?
Yes, and typically in wastewater, we said 40 meters per hour of backwash velocity. If we go with this 50-50, then you're on this 20%. Don't panic. Come to us, send us your data. You're working on a calculation tool which will do this long time automatically. In the meantime, you find it here, and beside this, you have us, especially Jochen. We don't like work, Philip and me.
Yeah.
And yeah.
So here, very important, maybe as a summary slide, here we talk about wastewater treatment. And again, here, different layer combinations. We really need more than 40 meters to evacuate and have the right bed expansion. Here you can see two different situations at 50-50, grade 1 and grade 2.
Blue.
So you need a little bit less of velocity to expand the bed. But if you go to a 70-30 bed, then you really need to have a higher velocity to expand it to that
And really,
level.
again, just to make sure, you don't have to do this because of AFM.
No.
If you have the same issue with sand, you need to do this in order to get the TSS out.
Exactly.
But nobody tells you. Nobody tells you, and if you don't have a side glass, you don't know it. But again, wastewater, we recommend 40 meters per hour of backwash velocity. Then we go with a 50-50 grading. If we are in drinking water where we only have 30 meters per hour, we go more for a 70-30. And if we are below, then we compensate it with grade 0 because we never reach the 25% of bed expansion. Don't mess around with this, just come to us. Who wants to go for this? We are again late.
So we mentioned, the absence of biofilm in AFM. That's why you can run an AFM filter at a slower backwash, 30 to 50 meters per hour. Sand in comparison, you would have to run at 35 to 60 meters per hour because you have that higher backwash velocity. Because you don't have biofilm, you can also shorten the backwash of AFM to 4 to 6 minutes, whereas with sand, you are at 8 to 12 minutes. So as a result of that, you will save a significant amount of backwash water. You can do the math here. So typically we're talking about 50% backwash water savings. You do not need air scouring. So
very important.
No air blowers, significant amount of energy savings.
Makes the process much simpler.
Absolutely.
And shorter, yes.
And really, really this speeds up your return on investment. Yep.
Good.
Case studies,
so this was all theory. Let's come to real life case studies.
So where do we start? South Africa, huh?
South Africa, Aqua Media, they made this project really nice. I think we showed it already. Nice Calplus filters, my favorite filters produced in Spain. Hello, Jan. That was your elevator speech. You see here what they achieved. It's a tertiary treatment of sewage effluent. They use it for irrigation, suspended solids, feed water 93, and then after filtration below 4, and E. coli 1,700 down to 0. So very well done. Bam, bam.
And of course, you can have different methods to remove suspended solids, like from RGF sand filters, pressure filters, moving bed sand filters, different drum disc filters. But all of them, they can remove, they have different performance of suspended solids removal. Here in this table, you can see the performance.
May I add something? And this is not a test we have done. Again, this comes from Spain. This was published in Technology del Agua, December 2019, page 47. And 2009, sorry. Yeah. And they compared this. And we,
well, you can see here that the AFM performs here really well. I mean, as a quick summary, first, we achieve a removal rate of more than 90%, 96% for TSS, turbidity, also 92% of turbidity removal. And also, if you look on bacteria count, we have a dramatically good bacteria removal because we filter down to 1 micron. Yes.
Yeah, but the interesting part of who is second best in class, you know, here it was RGF filters, you know, with quite a difference. Yeah. And here best was drum filters with quite a difference on the turbidity. And here it was second best, again, RGF filters. Yeah. Also, I mean, that also has to do something with velocity.
The velocity.
This was very, very low.
I mean, you can see we even achieved this figure with almost more than double of the velocity. Yes.
Yeah.
Here's
not we, but they did.
Yeah, they did with our AFM.
Okay. Back to wastewater again.
Here's another example. This one is from Israel. This is a project we've done 6 years ago, 5-6 years ago, I believe. Longer. So we had, I believe, 18 filters here. 14. They replaced 1 with AFM, and you can see the results here. You know,
so it's sewage water treatment.
Yes. Huh? Yeah.
And then I think decantation, and then it goes through the sand filters.
Exactly.
And they use this water for irrigation. Mm-hmm. And there are 2 values, limited and non-limited. Yes, if you are below 5, you can use it for limited irrigation. If you are below 2, they use it for non-limited irrigation.
That's exactly right. So you see the black curve is sand, which is just below that 5 NTU, which still qualifies for the limited irrigation. You see the performance of AFM. That was, right around 1 NTU, 1.2 NTUs on average. You see a couple of spikes there. This is when the turbidity meters,
the sensors
blocked.
Yeah. So you have these on sand and you have these on AFM.
Very good performance, factor of 3 better compared to sand.
Yeah.
Unfortunately, in this project, they didn't move forward with it because their sand was good enough in this case. Yeah. Right?
Now, there were 2 reasons. First of all, they complained and said, Dominic, I mean, filtration performance is great, but we have to backwash the filters more often. Well, ladies and gentlemen, that's the reality. You know, if you want to filter more, you have to backwash more often. We compensated this then on this point where we added the anthracite, and this is where we had the learning that this improves or increases the backwash times by a factor of 4. Then we were equal to sand. Yeah. So that was one of the complaints. And to be honest, I never understood it, you know, because they get a little bit more money for better, non-limited irrigation. But however, that was their decision. Yep. Anyway, it was for us an interesting case. This is one time where we did as Dryden a project on our own. I mean, really under our management, on our full responsibility. This is in Bangladesh. This is a textile company called Dirt. About 20,000 people are working in this. And there was already a project, I think it was from General GE Water, and the owner, he met Howard, and Howard convinced him, do it this way, that will be cheaper and that will be better and that will be a lot more sustainable. So we got, he brought back an order, big order to make a wastewater plant. To be honest, I was a little bit panicked. He said, don't worry, it will work. And it did, but it took a lot and
some gray hairs.
Some gray hairs. Here you see the process. Actually, it's 2 things. It's groundwater and it is wastewater. So it's 300 cubic meters per hour of groundwater. You made this here, huh? That is pumped up. Then we have our air diffusers. Philip, show our air diffusers.
Yes.
So we aerate the water to oxidize the iron and the arsenic which is in this with these air diffusers. I know they look very simple, but they are great.
Yeah.
I'm talking about the air diffusers.
Yeah,
Maybe
not me, not the guy who
we
holds
also
them.
look
Okay,
simple.
okay.
Maybe you're not great. Okay.
No, this
to,
is just maybe a word about these, right? So our air diffusers, they're heavy, they're ballasted, they sink to the bottom of the pit or the tank or the lagoon. They don't need to be bolted to the ground.
Yeah, if you're lower, if you're deeper than 3 meters, you need.
Then maybe, yeah. Or you put a weight on it. Huh?
Exactly.
Yeah,
just the weight. You don't need to bolt them down. So easy to move, easy to clean, because you just pull them out, you clean them with a rag, you throw them back into it. Very simple, very durable product.
But the beauty is they have 25% better oxygen transfer than any other diffusers that we know.
Yeah.
Okay.
And easy to install, retrofit.
Absolutely.
So super easy.
Yeah.
Absolutely.
But maybe we do once a webinar just about aeration, and we take our. So again, we aerated the water to oxidize the metals, to balance the water, and then this water overflow underflows to this, goes through AFM to filter it, to take out the particles, to take out the metals, and then it's softened. And so here we end up with clean and soft water. This also has an underflow. We backwash the AFM filters with filtered water. This is the grind water treatment. Can you stick on it? I like to have the control back. Let's go to the rest of the process. So this water then goes to the production. And from the production, you get the wastewater out. Let's have a look on the wastewater. This is this part. Very well done, your animation. I love it. So we have 300 cubic meters of wastewater. You know, there are 4 cubic meters of very strong dye, very hot, very polluted. Then you have 30 cubic meters of human waste. You know, there are 20,000 people. And then you have the normal dye water. And the different streams we pre-filter. Some with decantation, human waste with screw filters, the other things with drum filters. We want to filter it down to roughly 100 micron. Why? Because this water here still has a temperature of about 50 degrees, 45, 50 degrees. And this is too warm to start a biological process. So you would have to wait for a day or two. It's quite warm sometimes in Bangladesh until this cools down. Now, Howard, he has, of course, a brilliant idea. He said, okay, let's take here, this is the blue water, the filtered water that we need for the process, that we anyway have to heat it up to high temperature, which has only maybe 20 degrees. Heat this water up and cool the wastewater down. So with this, we have a big energy recovery. We are talking about 5 megawatt. So that's 500 liters of oil per hour, right? It's huge. That also made a big payback of it. And we can immediately start here, because we cool here the water down to 35 degrees, we can immediately start with the biological process. Honestly, this really killed us, you know, before, in the beginning, we had the big problems with blocking and so on. So I don't want to think back to this. To make the best environment for the bacteria, here we also feed in phosphates, we bring in a lot of nutrients, we balance the pH in the perfect level to start then with the biological process. And the biological process is 96 hours, 4 days aeration. So it goes in equalization, and then, well, these are just different pools, 7 meter deeps, where we have 500 of these air diffusers and where we just aerate it. And then it flows from one pool to the other, overflow, underflow. And by this, you're creating different species. And the one species is eating these pollutants, and the other one this, and end of the aeration tank too. You know, you have species who eat the other bacteria. So we are ending up with a very low sludge in the process.
And low COD, yeah, that's important. Yes, that's the reason why you do this. Yes.
Yeah.
1,200 to 100.
You take over here?
No.
It's your project or my project?
No. I try to...
No, to push me. Yeah.
Yes, a little bit.
Yeah, okay. I push you later on too. We talked about efficiency of air diffusers. You know, we have here 5 blowers. 1,000 cubic meter each. You know, each of them has 50 kilowatt. So if you get 25% more oxygen out or not, that makes a huge difference. We're talking about 250 kilowatt hours consumption. As you really clearly said, you know, the big part of the process just done by biology, just with this aeration. And we bring the COD from 1,200 to 100, and then we go through decantation, and then finally through the polishing step, again through AFM filters. Fantastic done. And here we end up with a COD of 20. We even could close the complete loop, but we don't want it to make it too precise. So thanks on this side really to our partners BioVista, who brought this project, who managed this project. Also thanks to our chief engineer that we hired there, Helmut Ols, who worked for us, and he made you see the installation, you know, Colplus filters, big piping, you know, GF fittings, very nice installation. Here you see the aeration, you see the huge heat exchanger, you know, they're bigger than the two of us. Okay. This is the water that we treat. From this, we get it to this. So here, Helmut pretends he drinks it. That's not really true. I mean, if you do, maybe you should rinse them with a bottle of whiskey. That might help to survive it. Yeah. Philip.
Okay. So next, let's talk about oil.
Now it's your time, guys.
Removal. Oil removal. I think Jochen, you have a short introduction slide here.
I have here a quick introduction. So
when we talk challenge you as well.
Yeah, of course. Yeah, I'm already expecting that. Yes, of course. Anyway, make it then short.
You provoked it.
So we have in the production of different type of oil, we have large molecules which are actually in the bottom area, which go then to the lighter molecules for different applications, like from gasoline down to fuel oil for big ships. That's different sizes of gas of hydrocarbons. So what does it mean? That means they have different specific gravities. So as higher up we go here, we have lighter oil or lighter hydrocarbons, and heavier are here. And that's actually giving you different viscosities at different specific gravities.
So I think it's the viscosity, right?
Exactly. So
the key one.
The key is viscosity, because viscosity kind of equal to sticking to the surface area. So we would say then viscosity of a fluid is actually the measure of a stickiness or the resistance to shear force. So that's very important because we talk about filtration. So we want to remove, in this case now, not solids. This may be kind of solids, but they are liquid. So we're removing them. So we have different API grades. That's the word you use for let's go back here.
API.
For API, for the viscosity, yes, centipores normally, but in the oil industry, you typically use the API, specific gravity. Then, of course, because you have heavier dispersed hydrocarbons, you actually have more dispersed in the water than the lighter ones, which are actually floating. That's very important for the removal process because you have then more heavier dispersed particles left in the process at the end, where you have finer, very fine particles. That's the key, because the finer particles we are going to remove with the media filtration. So that's actually the key, because the lighter ones, which are more volume, they are already removed with different flotation processes before.
Okay, now the Empire Strikes Back. I didn't understand it. Philip, did you? Or can you summarize
Not
it?
100%, but I guess
what's its takeaway?
The lower the velocity of the oil, the stickier it is.
Exactly.
The more difficult it is to
filter, yes.
To filter and to backwash, get it back out of the filter.
I mean, right? as heavier they are, as more sticky they are.
Yeah.
Yes. Yeah. And we have more of these sticky ones in the small particles, which we are going to remove.
So if they're heavy, I guess they're relatively easy to filter out, but they're really difficult to get out.
But heavy means high viscosity.
Exactly.
Right. I think that's something, at least, with my limited mental capacities, how I understand, and you tell me if I'm right or wrong, the more viscous it is, the easier it is to filter. But we talked about this, filtration is a process of filtration, holding them back, and to release them by backwashing, the more difficult it is to backwash.
Exactly, because the heavier oil,
that right?
That's right, perfect, yes. Just to mention as a conclusion is, heavier dispersed, they generate a lot of very small, fine particles, which we need to remove by filtration.
Mm-hmm.
Yeah.
Okay.
So let's
But
go
that
on.
means there is not the rule where you can say, like with groundwater iron removal, this is the iron rule.
No.
You have to do it case by case and see, okay, what hydrocarbons are we talking about? It's a small chain, so it's difficult to filter, but easy to backwash. It's a long chain, high viscosity, easy to filter, but difficult to backwash. So we have to do this case by case.
And you can see it here in the different oil applications. We have different oils. So we go here from recycled direct contact cooling from steel production. I think you will do some more details on that. We have other applications where we have, like in production of motors, of cars, you have more like a lubrication oil, oil well produced water, and produced water treatment. That's actually a big topic as well.
So first, I want to take you to the US. This is a project we've completed 2 years ago together with our partner in the US. This was for Nucor Steel. Nucor is one of the 2 largest steel manufacturers in the US. They're making mostly steel coils. And the application was for direct contact cooling water. So this is water that is sprayed onto the steel that comes out of the last steel mill, that is sprayed onto these coils to clean it from grease, oil, any metal particles. And it's actually the last cleaning process before it's shipped out to the customer. So very important. The goal was to reduce oil and grease, iron particles, and overall turbidity of the system. The challenges we had there really was they had only a very small footprint, so they didn't have space for large sand filters. It was important that the system would perform very consistently, so no breakthroughs, no big spikes in performance. And of course, as always, low maintenance and low operating costs were important.
What a surprise.
What a surprise. So the approach was a 2-step approach. First, we started with an on-site pilot, and then we followed with a full-scale filtration implementation. The pilot. So what you see here is the exact same pilot unit that we use. This is a pilot unit that we make, actually. It's a palletized system that allows you to exactly duplicate the situation that you have on site, because we have a variable speed pump, we have controllers, we have flow meters, so we can exactly control the parameters and duplicate any situation that we have or any situation that they want to test.
And you find them on our price list. And if you come, yes, I like it, but can I have it like this and this? No, it is what it is. If this is good enough, great. If you're not, do something on your own.
But there's really no need to change it.
Because that will always...
No, it contains everything. There is no need to have any
You just bring it on site.
But always comes the same question. Can I have a change?
Sure.
No.
And you plumb it in and you're done. And you see the pictures over here. This was after about 4 or 5 weeks. So, of continuous operation.
This is before backwash.
This was
below.
Yes. Obviously. Yes.
But when I read it, I said, okay, at least how it looks.
So this is
backwash.
how it looked, and this is how it looked after backwash. And these pictures came from the customers. I didn't take those.
So you didn't cheat.
So
if somebody cheated, it was Nucor.
Yeah, that's right.
But they went for the project.
But they were also backwashing at 50 meters per hour.
And this really, ladies and gentlemen, that's the key. It's not so difficult to filter the oil, but it's really difficult to clean it. And there are different technologies that we will discuss.
So the customer was extremely happy with the results. You see here, we see a turbidity removal rate of 88%. The red line is the turbidity out, blue line turbidity in. So you see that reduction here from 40 to 5. And this was at 20 meters per hour filtration velocity. So the customer came back and said, really, this is better than I need. So let me push the system. And what they did is they actually doubled the filtration velocity to 40 meters per hour.
Typical Americans.
Which they can with this system, right? Because it allows you to do it. And you see the removal rate dropped from 88 to still 80%. And the iron removal rate was still at 60%.
This is unbelievable.
So customer was extremely happy, and of course that was no surprise. They then followed with the full-scale implementation. They installed total of 8 filters, 4 filters in a row, vertical pressure filters with AFM. They decided to go with the backwash velocity of 20. So they have a little
filtration
bit
velocity.
Filtration velocity of 20. So they have a little bit of reserve safety margin built in, and backwash velocity at 50 meters per hour. This system is now running for 1.5 years, and the customer is extremely happy.
Yeah. Okay, so I hope we see soon a new order from it.
Yes.
So other application, we are looking into it and working together with a very famous company, oil and gas market. So here we don't talk about produced water. So we have primary treatment, we have a secondary treatment to remove the oil from the primary from 500 to about less than 200. After the secondary, typically you come out with a less than 100 ppm of oil. So that's where you typically apply in the produced water market, so-called nutshell filters. So here in this test with the customer, we were testing our AFM versus nutshells to see how much better we can improve the filtration process.
By the way, it was not we, they did.
Yeah, they did together.
We just helped them a little bit in the process because I don't want to get here the expectation, oh guys, you come and solve all our problems. No, you solve the problems. We just help you with the software.
Exactly. We help you with the software. AFM is used here. The customer did all of this very nice and very advanced installation to test the media in their produced water treatment.
And this was Sonic that we see later.
Exactly.
On.
Later on, we will see the company who has helped here to really provide these very nice installations.
They did.
They did it. Okay.
They didn't help. They did it.
Yeah. And we really have seen, and I will show that in the summary here in the next slide, that we have a very good oil coalescing, very good filtration, and important also attrition. So we have a much more longer expectation, lifetime expectation with AFM versus a nutshell. Yeah. So we can run our filters much more longer. Why is this the case? So here, go to this application where we have the produced water treatment. In this case, they wanted to test the back-produced polymer performance with AFM. In this first slide, you can see that that's just normal produced water treatment.
So to understand it, I think you're a little bit fast. You're fast for me, so I guess also for some viewers. And I'm just
going to explain it actually.
Yeah. So we have 60 ppm of oil coming in, and exactly. You have the back-produced water 0. So there is no polymer.
There's no polymer in that, yes.
Okay.
That means we just talk about pure oil removal in this application, yes. Here in this application, it's important to talk about fine oil droplets removal, because typically in this application, we talk produced water about particle size of oil droplets now, not on suspended solids, of in the range of 2 to maybe 15 microns. Again, 2 to 15 microns sand is not really perfect. Nutshells are much better in this application. That's why there is no sand used in this. That's why they use nutshell filters worldwide for the removal. You can see the performance is quite good with nutshells, but we already exceed the performance, or let's say we can say it's very similar to the nutshell, especially in this polymer, in this produced water application.
So why do you have here 52 and then you have 59?
So here they have tested it at different concentrations. So they went up with the concentration to 60 and to challenge it with 65. And you can see we are still reaching 1 to 2 ppm of oil in the outlet. Yes. And that's important. Is why do we achieve this? Because we remove much finer particles. Yes. And also because the surface area is much bigger.
But as a takeaway, I think we are here equal with nutshells.
Exactly. Equal, yes.
Equal with
and as I mentioned before, we have some other benefits, less attrition.
Let's come to that later on. But and what is the photo here? This is the...
Yes, this is the photo of the removal. So here you have the water, how it comes in before the treatment. This is actually before the first treatment process.
Yeah.
That's actually after the second treatment process. And this is the water coming out after our AFM filtration.
If you allow, just because I think you have done this so nice. So here, this is this water that we treat.
Yes, exactly.
It's not this water here. This is this water which goes.
That's why we have the primary, secondary, tertiary. That's the 3 bottles.
Yeah, well, and then we start here with this, huh?
Exactly.
This water, just not to make the dreams too big.
Exactly.
Right.
Yeah.
So what's the next one?
So the next one here we are testing, or they have tested, or we are testing. They are testing the AFM versus some back-produced polymer included in the produced water, in the produced oil water mixture. So here you can already see that the performance with nutshells is actually starting to drop. So only at 30 ppm of oil inlet, and that with some 100 ppm of back-produced polymer, they can only achieve 6 ppm. Why 6 ppm? Why Why did they limit the concentration? The reason is they need to have 5 ppm. I didn't mention it here. They needed to have a benchmark of 5 ppm as a maximum. So anything above 5 is not anymore fulfilling the requirements for the final water quality. So this is why they didn't go up to 60 with the nutshell, because already they exceeded the 5 ppm on the in this test. When they were using in the test our media, you can see we could even go to the same concentration as we had before, 60, 63 ppm, and we really remove the oil down to, even we have here, we just touched the bottom of 5, but with different type of combinations of AFM, that's different combinations of AFM they were using, we can achieve still 3 ppm.
Yeah, and I think really the takeaway, you see here, they test different medias, but also our AFM in different combination, grade 1, grade 0 in a combination, to find out what is the very, very best. So very impressed what these people have done. You know, they're great. I mean, the end customer as well as the technical company. But you see, the moment we already go with polymer, you have a huge difference.
Yes, and you see here the
nutshells are not achieving it anymore.
No, because again, droplet size, it's actually very similar to suspended solids. They talk about droplet size, as I mentioned before, between 2 to 15, and nutshells, they can actually, the cutoff is at best to remove 8 to 14.
If you add these polymers, you cut the droplets in smaller ones.
Yes, you have also, yes, you have smaller ones. You have, without back-produced polymer, you also have smaller ones, yes.
Yeah, but this is why with polymer, it's more difficult to filter.
Yes, because you kind of
water.
emulsify these oils, that becomes more difficult to be removed by filtration.
Good. Excellent.
Next one. So then they increase the concentration to 400 ppm back-produced polymer, which is actually what typically comes out of the production well.
So that's really what they.
That's
use.
actually at the end. That's what that's the benchmark they want to see. How good is AFM versus nutshells? As you can see here, nutshells, you can almost, I don't want to say forget about it. It doesn't work in this application, and we still achieve, even at 500, we can achieve a removal rate of 5 ppm or down to 5 ppm of oil in water.
So let's be nice. AFM perform by far better.
Yeah.
Okay, next.
So
here I want to say one word, because now it's your customer, but they started with me. Actually, we started here 3 years ago. I remember good time that we had in Scotland at that time. This is the company Sonic, who is responsible for all this engineering, and customer I do not want to mention. They're a great Austrian engineering company. And they develop these pilots, and they also do these filter systems, and they tested everything out. So this is, if you're in this, that's a company we really can recommend you. And they had really good results.
They provided the pilot unit, but they also built turnkey systems. That's important to know. They have some specific benefits, because what they have developed is like a new patented way of treating produced water in this specific application.
And really the very special thing is, you know, also we had problems, you know, they filter, I don't know anymore, at 10 or 15 or whatever velocity, not too high, but they also kind of backwash it very high, because otherwise they lose the media. They also use quite a big amount of grade 0. So the challenge is, how can you clean this AFM? And there was, you know, we see it later, you have high velocity, high temperature, or you have to bring in some energy. And this is exactly what they did. You see here these mixing elements, and then the retention filter up there. So I don't want to go in detail. I also do not know if it's secret or not. Go to Sonic, these are the specialists. But with this mixing, you know, they really mix the media very nicely in backwashing, release all the oil from the particles, have a security system that AFM is not leaving the filter. So fantastic what they did.
Really works quite well in the produced water treatment application.
So again, the challenge is filter, but even more to clean it. That's the big challenge. How you do that? And there are different technologies. Very impressive one is Sonic.
Yes.
Okay. We are over time.
Yeah,
because
we're
of
almost done. Huh?
I don't think
okay, so last we're going to take you to China, and really what we want to show you here again is the performance comparison between AFM and sand over a period here of 14 weeks. This was in a Chinese steel factory. We had about 100 ppms of TSS coming in. and we were using grade 1. So you can see that the performance of AFM is relatively stable at about 95% removal rate over that quarter, basically 14 weeks. You see the performance of sand, fresh sand that was brought in, also relatively good until it completely collapses at some point.
Gone.
Completely fails. And that was the sand that was in the system here. So very inconsistent already. Also, one thing to mention, the combination of sand and anthracite is not really a good idea when it comes to removing oil. One of the challenges that was mentioned is this here. How do you get your filter clean again? And you can see this. You have oil biomass accumulation. You have complete coagulation of the sand. That's a challenge.
Mess.
And I just want to mention one big customer of ours, Kaigon in China. They order anywhere between 1,000 to 2,000 tons of AFM per year that they install in oil fields. And they also always follow the same step. They have a short pilot installation, which you see here. And again, it completely confirms the data that we are getting anywhere else. You see the oil reductions here that we are getting. I mean, this was outstanding here in the pilot. And then in a second step, they go to the full scale installation. I was on this site here, and again, confirmation of what they're doing of the AFM performance. It really works. You can see this, the before and the after oil removals here, very consistent, very high level.
I mean, perfect. This fits to the figures we have seen before, from 60 ppm to 1 ppm.
Exactly.
But again, that depends on what hydrocarbon you have. If you have a very long chain, easy to filter, but difficult to backwash. So this is why here, I mean, it's really exciting.
You can see what's coming in here, right?
Yeah. Well,
it's the raw water. Of course, but this is heavy oil, right? So what's the takeaway here? Kaigon came back to us and said the key, very important, is the cleaning of the media. First, they backwash their filter at a minimum of 50 meters per hour. They actually try to go higher if they can. Second takeaway is that they can run these filters for about 8 to 12 months. And then the filter performance really goes down with AFM, right? Yeah. In comparison, sand, they were only able to run it for about 2 months. So now you have, a factor of 4 or 5 of a lifetime before you have to clean the media, which is significant downtime, all this, right?
Chemical.
Now they have developed a process of chemically cleaning the filter media at about 8 to 10 weeks, and they're actually months. They're actually working with 2 different systems now that they are exploring. One is an on-site offline media cleaning, so they shut the filters down, they take the media out, they clean it, they put it back in. And the other thing they're experimenting is an online media cleaning procedure that would allow them to mechanically and chemically treat the media. Exactly. They tell us that they found the solution. I can't wait to go down and see it. But
also, if there is a solution, probably that will be a secret.
We'll see how much they're able to share. Who
you are out there, in this field, you have to be a little bit pioneer. Absolutely. Trial and error.
Absolutely.
But we give you a very, very excellent software.
Yes. Okay. In summary, you have 3 cleaning options.
Yes, exactly. So first of all, velocity, we recommend really between 5 to 10 meters per hour. If you're above than 100 milligrams per liter of oil, which typically should be the case, go to 5 meters or less for velocity.
Filtration velocity.
Filtration velocity, yes. Andesite can be used, but actually it clocks quite fast. So it may be used in exceptional case where you have lower amount of oil. As you mentioned, this is the coagulation problem. It's difficult to clean. So backwash options with the oil treatment, you typically have 3 options. Mechanical cleaning, which you do in produced water. You have very specific filters, which is very intensive with shear forces and where some filters are removed, as we have seen, to help to avoid the loss of media.
So sonic would be here a perfect example.
Like sonic. Then we have cleaning chemicals, as we have just seen with Kaigon. You can use clean detergents cleaning. You can really do that, and that's done in the oil industry, or in applications where oil is removed. Or of course, also again, oil industry applications, hot water steam cleaning. That's also very often done. Yes, very important. Just to summarize, AFM performs much better than nutshells, which is one of the key product used in these applications.
Yeah. And usually in these applications, we use AFM standard. Go on back. We use AFM standard. It's not because it filters better than NG. It's the opposite, but it's easier to clean. Yeah. And yeah, one which I'm missing here, high backwash velocity. That helps.
That's the high backwash. You mentioned that before.
Higher backwash velocity, the warmer the water it is. So you have to find your economy and best way to clean it.
Yeah, but in oil, mainly what they're doing, they put in shear forces by mixing the media and have some filters here to avoid the loss of media.
Yeah, no, we talk. There is step number 1, and then the other is step number 2, which is a combination of high backwash velocity, poor water temperature, or detergents.
Yeah, exactly.
But it's up to you. Yep. We don't have the solution for you.
Good.
For the first one, call Sonic, or yeah. Good.
So we are at the end.
Contact him.
So please contact me. We want to hear from you, actually.
Absolutely. What do we want to hear from them?
What do we want to hear? Feedback on our webinars. So we are happy to receive your feedback on our webinars to know what did we good, what did we not too good. Again, today I can see 10 minutes overtime, but you're still here. We have still 93 throughout our...
So don't write this, we know this. What else?
Questions, inquiries. So any inquiry, please send it to us, questions to AFM. And of course, your proposal for future webinars. You would like to hear what would you like to hear from us for future webinars? Yeah, because we have done 4 and now we say goodbye, but we will be back. We will be back. I don't know when, but we will be back. In a couple of months, we'll be back. Maybe you know that. Is this you, Philip? Oh no, there's another guy. But I think he has the same accent. He looks. Okay. He looks good. Okay. We will be back. Definitely, we will do one webinar just about aeration, and here we want to have the help from Howard or his son Matthew, at least, maybe together with Mike or Michael. And according to your feedback, what would you interest? We will take this. We will inform you by LinkedIn, and then we will be back. Okay, next one. So Q&A. Now we are at the end. That was it.